Hey Calc 2 folks, welcome back to the next set of videos in our study of Chapter 10, which is going to focus in on the infinite series. If you haven't watched the first set of videos covering the sequence, you may want to go back and look at that material and become familiar with what it means to be a sequence. As we're going to see here in the study of infinite series, sequences are going to play a big role. To begin with, infinite series are formed when we take the infinite terms of a sequence and add them together, right? We see here in the definition, letting series a sub k equal, letting sequence a sub k equal the sequence of arguments starting at 0 and heading up to infinity with the values of their index, right? Letting a sequence a sub k be any sequence with an infinite number of terms. Adding the terms of the sequence produces an infinite series. And the way that we go about denoting an infinite series is we often refer to it as the value of s, where a capital S, where this capital S value is equal to a summation. Summation of values that starts at the index of k equal to 0 and continues up towards infinity, where we are summing the arguments of our sequence a sub k here, which does mean taking those values of a sub 0, a sub 1, a sub 2, a sub 3, and so forth, and adding them up. Right? If we look at an example, right, we might consider an example of a series, infinite series here. We might consider the terms of the sequence 1/2 raised to the kth power for values of k that start at 0 and head up towards infinity. Evaluating the sequence over these values of the index k, we would start at 1, and that would follow to be 1/2, and followed by 1/4, 1/8, 1/16, and so forth, right? What we might notice here is, yes, we do have a geometric sequence happening, right, where this happens to be a convergent geometric sequence. It is converging on the value of 0. Well, in this particular case, the corresponding infinite series would be stated as the value s equal to the summation from k equals 0 to infinity for the arguments of that sequence, 1/2 raised to the kth power, which is nothing more than starting with that term, that 0 term of 1, adding it to the first term of 1/2, adding that to the second term of 1/4, adding that to the third term of 1/8, and so forth, right? This continuing off towards infinity, that highlighted in the upper bound of our summation notation, right? Now, as for the value of s, right, some of you might have the intuition that adding an infinite number of values should result in infinity for that sum. Or if we think about the value of s, that s should head off to infinity. But I will tell you that there are some interesting situations, right? If it's the case that the sequence we're looking at is bounded, right, there is a possibility that the corresponding infinite series is going to actually be finite in value. That is, this value of s that our series represents is going to approach the value, is going to approach a real number value, right? To determine the behavior of s, whether it's what we might say heading off towards infinity or approaching a real number value, to study that behavior, right, we study the behavior of the sequence of partial sums, right? And we study the sequence of partial sums for either what we call convergent or divergent behavior. Now, what is the sequence of partial sums? If I bring that definition into view here, by definition, right, we might say here, suppose S is an infinite series, right, where the series begins the summation at k equal to 0 and heads up to infinity for a sub k. The corresponding sequence of partial sums is going to be given by the sequence S sub n, where S sub n capital S sub n is going to equal the sequence S sub 0 followed by S sub 1 followed by S sub 2 followed by S sub 3 and so forth. Where when we think about the formulation for S sub n is going to be equal to itself a summation. A summation that also starts at an index of k equal to 0, but only continues up through the value of n. All right? N equaling 0 for the 0 term, n equaling 1 for the first term, n equaling 2 for the second term, and so forth. Right? Where this summation is going to occur over the arguments of our corresponding series A sub k, right? And will illustrate nothing more than a finite summation, a summation that starts at A sub 0 and continues up through the argument of the sequence A sub n. Right? That's going to define for us what we call our sequence of partial sums. We study this sequence of partial sums to look for either convergence or divergence, and depending on the behavior of the sequence of partial sums will help us to make some conclusions about the behavior of S. If we go back and we look at our example, and we consider again the summation for S that's given by 1/2 raised to the kth power, where we're summing from k equals 0 to infinity, right? The sequence of partial sums is going to be given by the sequence S sub n, where in this case S sub n is going to be equal to the summation from k equals 0 to n for 1/2 to the kth power. If we elaborate further, this does have the implication that sequence S sub n will be equal to S sub 0, comma, S sub 1, comma, S sub 2, and so forth, where that 0 term, S sub 0, would be our summation from k equals 0 to 0 for 1/2 to the kth power, which is nothing more than just the value of 1/2 to the 0 power, or the value of 1. All right? That would be the first term, or what we might call the 0 term, in this sequence of partial sums. As for what would actually highlight the first term, that would be S sub 1, its value, we'll take note, would be given by the summation from k equals 0 to 1 for 1/2 raised to the kth power. It would be equal to 1 plus 1/2, which with a little simple arithmetic we can note is 3/2 in value. That would be this value S sub 1 found in our sequence of partial sums. If we continue for S sub 2 and S sub 3, S sub 2 would be this summation from k equals 0 to 2 for 1/2 k, which would be adding 1 to 1/2 and then adding on 1/4, the case for k equal to 2, which would produce 7/4. And for S sub 3, S sub 3 would be the summation from k equals 0 to n for 1/2 k, which would take 1 and add 1/2 and add 1/4 and then add 1/8, which in the end would total to 15/8. This would continue on, right, and so forth. So in the case of the sequence of partial sums, we might say that the first, 1, 2, 3, 4, 5, 6 terms, right, would be the values 1, 3/2, 7/4, 15/18, 31/16, 63 32nds, and so forth, heading off towards infinity. All right? And as we had noted, this sequence of partial sums can be examined to help draw some conclusions about the value of S. Right? As for the value of S, in this case, S equal to that summation from k equals 0 up towards, I have a notation error there, infinity, right, for 1/2 raised to the kth power, this would depend upon the convergent or divergent behavior for the sequence of partial sums. By definition, right, if we define convergent or divergent behavior here, right, for the series, By definition, letting sequence S sub n be a sequence of partial sums for series S, if the limit as n heads to infinity for that sequence of partial sums converges to L, some limit value that's contained in the real number system, then what we can conclude is that S will also converge. And that would be convergent on the value of L. Then S will also converges, we might say here, on the value of L. Right? Where we can further go on to say that the value of S, right, this summation from k equals 0 to infinity, I can see I have some copy-paste errors in there, is going to be equal to the value of L. Whereas if our limit as n heads to infinity for our series diverges, right, then S is also said to diverge. Right? So, as we can see here, what this definition sets up is what we call the convergence or the divergence of our infinite series S, which can be determined by examining the limit as n heads to infinity in the sequence of our partial sums for the series S. If we go back and we consider our example in this set of notes, this example of S equal to the summation here from k equals 0 to, again, infinity from k equals 0 to infinity for 1/2 raised to the kth power. Our sequence of partial sums will be given by these values here, where if we take note in the pattern in this sequence of partial sums, the pattern for the sequence S sub n can be stated as the explicit formula illustrated here. S sub n, you might recognize, is essentially the ratio of 2 to the nth plus 1 power minus 1 over 2n, which with a little bit of algebra, right, you can rewrite to state as 2 minus 1 over 2 to the nth power. Now, in this result, we see a nice result where the application of a limit can be applied, right? Where if we now think about the limit as n heads to infinity for the sequence of partial sums, well, we can consider that the limit as n heads to infinity for 2 minus 1 over 2 to the nth power. Now, that limit will distribute itself across this difference. The limit of 2 would be 2, the constant, whereas the limit of 1 over 2 to the nth would head to 0 as the value of n heads to infinity. That denominator growing without bound would cause the value of 1 over 2 to the nth to approach 0. So in the end result, we would have 2 minus 0, or the result equaling 2 for the limit of the sequence of partial sums. Now, what does that all mean? Well, that means, first of all, that sequence of partial sums converges to the value of 2, right? And if we're able to conclude that sequence of partial sums converges to the value of 2, we can further go on to conclude that infinite series also converges to the value of 2. Or that when we think about the value of S being the summation that goes from k equals 0 all the way up to infinity, right, for the quantity 1/2 raised to the kth power, that infinite summation actually doesn't grow without bound. It actually converges on a particular value, and that value is the value of 2. All right? So that is, to begin with, an introduction to infinite series, folks, and the study of infinite series. We started off with defining what is an infinite series, and following that up with looking at whether or not that series converges or diverges in value, whether or not we're able to say that an infinite series actually equals a number, or whether or not we have to say that series diverges off towards plus or minus infinity, by studying the sequence of partial sums and their limit, right? And as we've noted, if the limit for the sequence of partial sums converges on some real number value, right, we can conclude that the corresponding series will also converge on that real number value. Now, I do have a couple more videos in this infinite series, in this set of videos covering the infinite series to go over with you folks. One of those being a study of a couple of particular cases, and that being the geometric series, which I've already highlighted when we were discussing geometric sequences. And then there's also another unique case for series where we look at what we call telescoping series, right? We're going to spend a little time looking at telescoping series. And then along with all of that, we have a couple of properties of series that we want to make sure that we spend some time taking note of, right? They are some useful properties. So I do have a few videos following this one where we'll get into those ideas. So hope you join me then. Talk to you later, folks. Bye. Hey there, Calc 2 folks. Welcome back to my second video in my set of videos covering the study here of series, where we're going to spend just a moment taking note on the geometric series and some interesting results we have for this series. To begin with, geometric series is formed when we have a geometric sequence and we add up the terms found within a geometric sequence. All right? This is what we see given to us by definition. If I bring up the definition here, right? By definition, letting sequence a sub k equal the geometric sequence a times r raised to the kth power, a being the what we call zero term, r being again the common ratio, right? The corresponding geometric series is given by the summation of those terms, summing from k equals 0 up through infinity. Now, where we have some interesting results, if the absolute value of our common ratio is less than 1, we do note that our geometric sequence would be convergent and it would converge on the value as 0. But as for our series S, the geometric series S would also be convergent, but in this case it would be convergent where S would converge on this value A divided by 1 minus R, right? What we see here is an actual formula that we can use to determine the value of an infinite geometric sequence in the case for a convergent value of that. Well, I should say for the case of an infinite geometric series when that series is convergent, right? And that does happen when the absolute value of the common ratio is less than 1. Otherwise, if the absolute value of the common ratio in a geometric series is greater than or equal to 1, what we have is the result of that series being divergent. The value that S would sum up to would either be plus or minus infinity. It would diverge off in the infinite direction. All right? If we look at some examples, right, we might start off with our first consideration, right? Again, where S here would be equal to the geometric series given by the summation from k equals 0 to infinity for 1/2 raised to the kth power. In this geometric series, again, our 0 term A would be equal to 1, and our common ratio R would be equal to 1/2. Furthermore, we could note, since the absolute value of R would be equal to 1/2, which is less than 1, the value we understand as S would have to converge. Where when we think about that value of S, it could be calculated using that formula A divided by 1 minus R, where in our case, again, A is the value of 1. That goes in the numerator. And in the denominator, we take the difference of 1 with our value of R, 1 minus R. 1 minus R, or 1 minus 1/2 in this case, produces 1/2. And 1 divided by 1/2 is 2 in value. All right. If we look at another case of a convergent geometric series, we might consider this series here that's convergent. All right. In this case, S is equal to the summation from k equals 0 to infinity for 3 times 1/4 raised to the kth power. Again, this is first of all, a convergent geometric sequence whose terms we're summing, right? In this case, A would be equal to 3 and our common ratio would be 4. And again, since our absolute value of the common ratio r is equal to 1/4, which is less than 1, what we know about this geometric series S is that it also has to converge. Where if we think about the value of S, again using that formula a divided by 1 minus r, that would produce 3 divided by 1 minus 1/4, which would equal 3 divided by 3/4. With a little arithmetic, we could show is equal to the value of 4. All right, so folks, this is just a quick little study on geometric series where we do have some interesting cases in this series, that being the case when our common ratio here, its absolute value is less than 1, where we have a convergent geometric series. And we have this formula a divided by 1 minus r that allows us to find the value of that series. One thing I should probably go back and point out, this is for the case of a geometric series, though, that starts at k equal to 0 and heads up to infinity. Certainly, our sequences can start at any index and head off towards infinity, meaning that we can have a series start at any index and head off towards infinity. But in regards to this formula here, a over 1 minus r, it is only true for a geometric series that is in this form with a starting index of k equal to 0. We might look at some examples in a couple of future videos where we certainly change around perhaps our starting index value in the series. So folks, that is geometric series. I have a couple more videos to go through with you, and I'll be back then. See you then. Bye. Hey there, Calc 2 folks. I'm back with another quick portion of the lecture here on infinite series, where we're going to spend some time looking at the telescoping series. Telescoping series are a unique case of series, very much so like the geometric series, where with a little bit of algebraic method we can determine the exact value of this infinite series. This doesn't happen too often with the case for infinite series, but the geometric series and the telescoping series we're going to see are some unique cases where we can actually just use a little bit of algebra and determine the exact value of the series. Now, what is a telescoping series? Well, these are a little hard to define. They're easier to see if we look at some perhaps examples. Okay, folks. So I do first of all start off by presenting you with the infinite series given here for S, where you can note S is the summation from k equals 1 to infinity for the sum of 20 divided by 25k squared plus 15k minus 4. All right. As we can see here, certainly this is a sequence inside this series, whose format we haven't seen too many examples similar to yet. But we do take note that it is a rational form, and more so, that it is a proper rational form. That is, the degree of the numerator is less than the degree of the denominator, right? The degree of the numerator being 0 in degree, whereas the degree of the denominator being 2 in degree. We worked with proper rational functions or arguments back in chapter 8 when we were looking at fractional decomposition and taking a proper rational function and breaking it down into, or decomposing it in a sense, into a sum of what we call partial fractions. If we do that in this case, what we will do is to this rational argument is we will make it a little bit more obvious and give it a little bit more explicit nature to that telescoping form that we're going to see here in this case. So we'll bring into view here some note. What we do have here in this infinite series is a telescoping series, but it is being expressed in a bit of an implicit form. Performing a little fractional decomposition and expressing this argument as a sum of partial fractions will help to actually reveal the telescoping series in its explicit nature. right? If we perform the decomposition, right, I'm not going to go through the decomposition here. This was a technique that we discussed in Chapter 8. It is algebraic, that you should be familiar with it. But what we do find, if we were to perform that decomposition, is that this proper rational argument, 20 over 25k squared plus 15k minus 4, when decomposed, will turn into the sum of partial fractions given here on the right-hand side. 4 over 5k minus 1, all minus 4 over 5k plus 4. All right. This would be the decomposed form for the argument we see inside of our infinite series. Now, what this decomposed form illustrates is a telescoping behavior. To illustrate what I mean by a telescoping behavior, let's take note of what would be the behavior seen for this infinite series if I was to express its argument in this explicit form, right? If we note, as we go from k equals 1 to infinity, notice the behavior of the arguments for each round or each iteration of our values of the index k. At k equal to 1, 5 times k would be 5 minus 1 would result in 4, and we'd have 4 over 4, which we'll see does simplify down to the value of 1. But that is followed by minus 4 over the quantity of 9, minus 4 ninths. When we substitute in the value of k equal to 1 into this argument, it does produce 4 over 4 minus 4 ninths. Where that's not very interesting until we consider adding on our second term. When we add on to this our second term, the case for k equal to 2, right, we will see that the 4 over 5 times 2 minus 1 will simplify into 4 ninths, and that will be, we'll subtract from that the quantity 4 over 5 times 2 plus 4, which would be 4 fourteenths. Where if we pair this second term in our infinite series with the first in the summation, we will notice what happens here is this minus 4 ninths from the first term is going to cancel with the positive 4 ninths from the second term. Now notice if we continue with k equal to 3, this produces our third term for this infinite series, this quantity 4 fourteenths minus 4 nineteenths, where the first term in this quantity would cancel with the second term in the previous quantity. Negative 4 fourteenths added to 4 fourteenths would turn into 0. And what you will take note, if you continue through our iterations of k from k equals 1 to infinity, this cancellation of first terms in an iteration of this series calculation with a previous term will have this canceling effect all the way down the line up towards infinity. In a sense, when we think about the value of this series S, this is really maybe thought of as 1 plus some ... value. It really does depend upon what's happening here way out at the end of this infinite series. Certainly we can see here after the value 4 over 4, every term along the way is going to cancel. So what does that mean for the value of S? And you might have a rather intuitive feeling for what that might actually mean. Let's see it happen through a limit exploration. To explore what happens, what we are going to see or look at for this value of S is the behavior of the sequence of partial sums for this series, and more specifically the limit as n heads to infinity in the sequence of partial sums. If we take note on that value in this case, right, the sequence of partial sums, if we were to add that up from term for the case of n equal to 1 to n equal to 2 to n equal to 3 to n equal to 4 and so forth, S sub n would take on this format. For the first term, it is 1 minus 4n, right? We can see that just given right here, 1 minus 4n. But if we were to add on to that the second term and consider the term in the sequence of partial sums for the case of n equal to 2, that would be this first term added to this second term, where certainly those middle, that minus 4/9 and that plus 4/9 would cancel, and we would have the quantity 1 minus 4/14 for our second term. That pattern would continue for the third term, the 4/9 canceling, and now the 4/14 canceling, leaving us with 1 minus 4/19. And this pattern would continue on up indefinitely, towards infinity. Now, what does that mean about the value of S sub n? If we take note of what would be the explicit formula for S sub n, right? The explicit formula for S sub n could be argued to be this value, right? If we are summing this sequence of partial sums from k equals 1 to n, this summation will start at the case for k equal to 1 and continue up through the case for k equal to n. Now, what we will see in that pattern along the way is that these quantities in between the very first term and the very last term in this argument for S sub n would cancel. 4/9 canceling with minus 4/9 canceling with positive 4/9, minus 4/14 canceling with positive 4/14, minus 4/19 canceling with positive 4/19, and that pattern continuing all the way up to this quantity of 4/5 times n minus 1 canceling with a minus 4/5 n minus 1 in what would be the previous term. What would remain then is just this minus 4/5 n plus 4. So when we think about the sequence of partial sums in an explicit formula, it is the quantity given by just 1 at the beginning of this the summation minus the quantity here 4/5 n plus 4, the quantity found at the end of the summation, with everything along the way canceling or adding up to the value of 0. So what does that mean about our limit? And this would have maybe felt a little intuitive in terms of behavior. If we consider the limit as n heads to infinity for S sub n, then that is just going to be the limit as n heads to infinity for this explicit formula. Where as n heads to infinity, the value of 1 will certainly just remain 1. Whereas the limit as n heads to infinity in this this ratio of 4/5 n plus 4 would actually head to 0. As that denominator grows without bound, 4 over that denominator will actually head towards the value of 0, leaving us with the result of 1 minus 0, or the value of 1 for this telescoping series. All right, folks, this is telescoping series. I don't think, do we have any other notes? Yes. What we can finish up with here, what we can actually then conclude, right, is that since sequence S sub n converges to the value of 1, that the value of S must also converge to this value of 1. Or that if we think about the actual value of S given by the summation of this proper rational argument involving k, that does equal this value 1, right, in its sum. This again illustrates telescoping series, folks. This case doesn't initially appear as a telescoping series. It's not until we write it as a sum of partial fractions back here at the beginning, when we think about it as the sum of partial fractions, that we start to see this telescoping behavior in the terms of the series. And what we mean by this telescoping behavior is, as we progress from term to term in the series, we have values of the terms canceling, or values within each term canceling, to the point where we can actually look at and see a pattern, right, develop in what would be the sequence of partial sums. We can then evaluate the limit of that pattern. Oh, scrolled to the left here. Right? We can then evaluate the limit of that pattern, right, and the explicit formula for that pattern, and develop a value for the actual infinite series itself. All right. Again, folks, this is a unique case of infinite series where we can actually determine the actual value of the series. this doesn't happen that often, folks. There isn't that many instances where you can actually determine the true value of an infinite series. What we're often going to find is that we're going to have to rely upon some approximation techniques. And we will develop those approximation techniques in some future videos here, folks. But the geometric series and the telescoping series are two specific cases where we can rely on just these algebraic methods to find the true values of S. Folks, that ends my third video, I would say, in this series of infinite, this lecture series on infinite series. I do have one more topic that we want to run through. That is some properties of infinite series. I'll come back with that video here in just a bit. But I hope you're all doing well, and I'll see you in a bit. Hey there, Calc 2 folks. Welcome back to what I hope is the last video in the set of videos covering the infinite series. One last thing that I wanted to look at with you is some properties of convergent series. And these are presented in theorem form, and I do believe there's 5 of them that we're going to see here. And following up with these properties, I do have a quick little example that I'm going to run through with you that helps to illustrate these properties. So, to begin with, like I said, these properties are presented in theorem form. The first property here is are already in view, right? And it just says, suppose that you do have a convergent infinite series and that it converges on the value of A. Letting C be any constant, then what is also true is that a constant multiple of the arguments in a corresponding infinite series will also be convergent, and the values that they will converge on is the constant multiple times A, right? In a sense, a constant multiple of the arguments of the series does not change the convergent behavior of the series. It will still be convergent, and intuitively it would be C times the value the original series converged to. One thing you will note in these properties that we're going to see is that this lower bound of K is not going to have any specific value. This is true really starting at any lower bound of the index of a series. We will see this continue throughout our properties. It doesn't matter if this is a series that starts at K equal to 0 or a series that starts at K equal to 10 and continues up to infinity. This property will always be true for any infinite series with any lower bound, right? If we bring up the second property, right, we see a similar statement, but with respect to the divergent behavior, right? If we have an infinite series that diverges, letting C be any constant, if we then take a constant multiple of that divergent series, that constant multiple of the divergent series will also be divergent. It's also going to diverge in value. Both of these being rather intuitive results. If we bring up a third property, right, something that might feel rather intuitive, right? That says, suppose you have two convergent infinite series here, one of them converging to A, the other converging to B. If you were then to form a corresponding infinite series involving the sum or difference of the other two in our assumption, then the result itself would also be convergent. And what it would converge upon is the sum or difference of the results in the individual infinite series, right? In a sense, this summation notation will distribute itself across a sum or difference, and the result for the sum, for the infinite series of a summation is really just the sum or difference of the individual infinite series results, folks. So again, this is a rather intuitive property, so we take note. And then we have a property that plays off this for property 4. Right? Suppose we have one infinite series that diverges, and we have another infinite series that actually converges, right? If we then go and take the sum or difference of these two individual infinite series, the one that diverges and the one that converges, the sum or difference will be a divergent result, right? Regardless of one of the series being convergent, if the other series diverges, then the sum or difference of those two series will also diverge. All right, so that is our fourth property in the list. And if we bring into view our fifth and final property, all right, it should be coming up here. All right, the fifth and final property states is that for any positive integer m, right, m is going to play this role of a positive integer. The series given by k equals 1 to infinity for a sub k and the series from k equals m to infinity for a sub k either both converge or both diverge. What you will note is what this property is saying is it doesn't matter what your lower bound is in your series, right? Changing that lower bound in your series from one value, and for instance the case for k equals 1, to some other value for the case of k equal to m being any other positive integer, right? Both of these series are either going to both converge or both diverge in value. Changing this lower bound does not change the convergence or divergent behavior of the series. All right, so we do have these 5 properties related to the convergent behavior of series, and more specifically really the convergent and divergent behavior of series, but we just summarize these as properties of convergent series. What I might give you here at the end is a quick little example illustrating some of these properties. Let me bring that into view. Right. As I said, to explore some of these properties, we'll see some of these properties used in the following example. Assume a ball falling from a height of x feet rebounds to a height of 0.8 times x feet. In a sense, what we are highlighting here in our assumption is that we have this falling ball that when it rebounds, it's going to rebound to what we might think of as 80% of the height that it had fallen from. In this particular case, the distance traveled by the ball, right? What we want to consider in this problem is determining the distance traveled by the ball if the ball happens to be dropped from a height of 20 feet. Now, if we let S describe this distance can be calculated using an infinite series. All right? That infinite series being this calculation for S here, where when we think about the value for S, we are going to have the initial 20 feet that the ball falls before it bounces and rebounds. When it rebounds, it is going to rebound 80% of that distance of 20 feet. So it is going to rebound back up to a height of 80% of 20, which would be 16 feet. But one thing we want to remember in the problem is that it's going to have to then fall that 16 feet again, or that 80% of 20 feet, where it then is going to bounce again 80% of what we had in terms of this falling distance of 16 feet, and that would be given by 20 times 0.8 times 0.8, where really what we would have is 20 times 0.8 squared. Now this is the rebound height, where then we would fall back down to the ground this given distance. 20 times 0.8 squared again, and this pattern would continue off towards infinity. As for this value of S, one thing we can note here is we really are maybe perhaps looking at the sum of two individual infinite series. And in fact, to consider its calculation, that is how we are going to approach this problem. If I bring up a bit of a note here, we might take note. Right? Again, that S does appear to be the sum of two convergent geometric series, where if we think about the value of S sub 1, S sub 1 in this series is the sum of 20 with 20 times 0.8 with 20 times 0.8 squared and so forth. right? It is the summation from k equals 0 to infinity for 20 times 0.8 raised to the kth power. Whereas the second value of s sub 2 found in this calculation for s, it is also a geometric series. If we think about its geometric series, it is the corresponding geometric series given by 20 times 0.8 plus 20 times 0.8 squared plus 20 times 0.8 cubed. It is perhaps this term in the series plus this term in the series plus the 20 times 0.8 to the third power in the series and so forth. Right? It is this corresponding geometric series. Now notice these, hold on here. I should correct that. That should be a power of x up there, not 3. But it is this corresponding geometric series here. Now, notice they are very similar in value, right? Where they really differ from each other, S1 and S2, is in this lower bound. Here, this series starts at a lower bound of k equal to 1, and this series starts at a lower bound of 0. Right? But one thing we would point out is they are both convergent geometric series. Both of them do involve that common ratio of r equal to 0.8, whose absolute value is less than 1. So if both of these are a convergent geometric series and we consider the series formed by summing them, that series itself will also be convergent. In a sense, we are putting into to play here a theorem 3 up here in our property 3 up here in our theorem for the property of convergent series, right? So when we think about S being the sum of the S1 and S2, we are using that property, where here S1 and S2 are going to be these two individual convergent series, right? And one thing we ought to maybe note is these two convergent series are very similar in behavior. The only thing that differs is their lower bound. Again, that might help to highlight property 5 here and what property 5 is saying. Here we have two very similar looking series where really the only difference between these series is the value for this lower bound. And in either case, both series are going to either converge or diverge. Changing this lower bound from 0 to 1 or from 1 back to 0 really has no effect on the infinite, the value of the infinite series and the convergent behavior. In fact, if we think about calculating these values, what we would go back and note is because they are convergent geometric series, we can rely on a rather helpful formula that we saw back for the case of geometric series. For the value of S sub 1, right, if we bring that into picture, we might note S sub 1, right, is the case for a geometric series where A is 20 and R is 0.8. And since it is convergent, right, the absolute value of R equal to 0.8 being less than 1, we are able to use that formula given here where we take A and divide it by 1 minus R. A divided by 1 minus R in this case is 20 divided by 0.2, which when we calculate that quotient, we do result in the value of 100. Right? That is this value for S sub 1. Right? If we consider the value of S sub 2, now S sub 2 is going to look a lot like S sub 1, except it's missing the 0 term. When we think about the value of S sub 2, right? S sub 2, as I said, is very similar to S sub 1, except it starts at k equal to 1 as opposed to k equal to 0, which does mean that we are, in a sense, looking at the summation for k equals 0 to infinity, but subtracting off here the corresponding definitive summation from k equals 0 to just 0. In this case, what we might think of is we do have this summation given for S sub 1, but we are subtracting away the very first term. What is the very first term in S sub 1? We can go back and note that very first term being 20. S sub 1 and S sub 2 look very similar to each other. The real difference between S sub 1 and S sub 2 is this very first term. S sub 2 does not include this quantity of 20. So when we think about S sub 2's value, right, S sub 2 can be thought of as the value given for S sub 1, which is 100, minus the quantity given in the very first term of S sub 1, or the zero term, the case for k equal to 0. And that is going to be 100 minus 20 in value, which results in 80. So in this particular problem, right, we're able to conclude that the distance traveled, or illustrated by series S sub 1, is 100, and the distance illustrated by series S sub 2 is 80. So the total distance traveled by this rebounding ball in this scenario, and under our assumptions, is going to be a total distance of 180 feet, folks. Right? This is a neat little example that highlights infinite series and some perhaps we might call real-world application, even though this is highly unlikely a real-world scenario where we consider this ball that kind of bounces forever, right? But if we were to remove some of the other assumptions of physics and just consider this as the conditions of the problem, this would be a case for where we would consider an infinite series that does have a convergent result to it. All being able to be calculated with, first of all, some properties of infinite series that we make use of, or properties of convergent series that we took note of in the beginning of this little quick video, and making use of what we understand with respect to the calculation of geometric series, and that calculation given by the quantity a over 1 minus r. So folks, I do think this ends my my lecture notes over infinite series. These put together with your sequence notes really do cover the first 3 sections of chapter 10. If you go through and you look at those first 3 sections of chapter 10, it is an introduction to kind of the study of infinite series that we're going to look at throughout this chapter, and then gets into some of the details of chapter of the topic of sequences individually and the topic of infinite series individually. I've kind of combined that 10-1 into my discussions of just sequences and series. So hopefully you have understood these lectures, and if not, we are going to have some opportunity to meet as a class on Collaborate, and we can always address some of those muddy points that might still exist in these lectures. So folks, I am thinking of doing, I might be able to put together another quick Mathematica demo. I did put one together for sequences. I might consider, is there something I could illustrate here with series, but no promises, folks. It's been a long day, and I'll see what I can get together as we head into the return from spring break. So I hope you're all doing well. This does conclude my lecture on infinite series, and what we are going to come back to in terms of a lecture, some follow-up lectures here, is we are going to be looking at some tests for convergence. As we had noted, the geometric and telescoping series are really our only 2 unique situations where calculating the value of a infinite series can be done with just a little algebra, or in some cases even maybe arithmetic. Whereas in a lot of cases, we're going to have to rely on some approximation techniques. Now, or other techniques in general, just an exploration of the sequence of partial sums and the limit for the sequence of partial sums. As we're going to see, this is sometimes a rather tedious, cumbersome task, and that it's not necessarily something we want to waste our time on if we are happening to be dealing with a series that isn't convergent. If a series diverges, it's not going to sum to any particular value. So to spend the time trying to approximate that value, or to spend the time trying to explore the sequence of partial sums, would really be a waste of time. So what we are going to see here in some of these follow-up lectures are some ways of testing a series to determine beforehand whether or not it is convergent or divergent. All right, folks. Again, I'll stop talking for now, and I'll see you in the next lecture. Have a good one. Bye.